I'm Mitch Roddenberry. I'll be talking about invariant graph neural networks for trajectory prediction, which is work with Glaze and Santiago Segarra. Convolutional neural networks are popular architectures composed of a sequence of filters, pooling layers, and nonlinear activation functions for processing images, such as this cat here. Similarly, graph neural networks are composed of a sequence of local aggregations or diffusions and activation functions for processing data on a graph or network. A key property of convolutional neural networks is their shift invariance. If you take an image and shift it to the right and up, that image is essentially equivalent in that the output of the network will remain the same. Similarly, graph neural networks are permutation invariant, so if you rearrange and relabel the nodes of a graph, the output will also be the same. A key thing to note here is that enforcing appropriate symmetries helps with generalization of these architectures. A particular type of data we're interested in is flows on graphs. Let's consider a graph and indicate a flow on it by a set of oriented edges labeled blue here. However, if you change the orientation of the edges, you can actually represent the same flow just by changing the sign of the data on those edges, so that the blue flow on the left and the red flow on the right are equivalent. And in fact, you can mix and match this however you like, but the skew symmetry of flows tells us that the data does not depend on the chosen orientation. Well modeled by flows is trajectory prediction. That is, given observations of an agent moving along a path, we want to predict where that agent will move locally in the future. When designing neural network architectures for trajectory prediction, our hypothesis is that incorporating the skew symmetry of flows and making it invariant to chosen edge orientations will help with generalization. So to test this, we create a synthetic data set supported on this graph with 2 holes in it. For training data, we consider a set of trajectories that go from the lower left corner to the upper right, bending around the upper left corner. And then for test data, we consider another set of trajectories over a disjoint region of the graph, going in the opposite direction. We evaluate the prediction accuracy in the trajectory prediction task for both non-invariant and invariant graph neural networks. On our training data, we see that there isn't a huge difference between the performance of the non-invariant and invariant architectures. But as soon as we try to generalize to unseen data over different regions of the graph and going in different directions, we see that the invariant architecture doesn't suffer much, but the non-invariant architecture fails because the rule it learned was dependent on the orientation of the edges, while the invariant one was not. This reinforces our key point. Enforcing appropriate symmetries in graph neural network architectures helps with generalization. I'd like to acknowledge the NSF, Army Research Labs, the Kennedy Institute, and ExxonMobil for their support.